Good afternoon, everybody. Welcome to the next segment of the Signals and Systems class. Looking at how far we got, I probably am going to make a change and do some more of the This Is stuff today and have you read through the notes, and we'll do the how-to stuff, or we'll introduce the how-to stuff in class on Tuesday. So what I'm going to do is I'm going to screen share and show you the notes that I started using yesterday. So you now should be able to see the notes. And this is what I covered yesterday, although not everything that we covered is actually in those notes. But anyway, so we covered the first several pages. And what I'll do is I'll jump down to what we had covered. And basically, what we had done is we'd got to the end of continuous time signals, and we'd introduced the idea of sampling. So now I want to talk a little bit about the definition of discrete time signals. And there's a couple of ways of doing the definition. We could either specify a rule for calculating terms, or we can note them explicitly. And throughout the semester, we'll use both methods. So I start by an example where we can specify the value of the nth term, and then I just write out the sequence of terms. And then I go on to show you how we can just specify the sequence. And in that case, there's going to be a term for which n equals 0. And to denote that term, we do it with a up arrow below the specific term. And you can see in both of these, we have the up arrow. If there is no up arrow, then the first term in the sequence corresponds to n equals 0, and all of the values are 0 for n less than 0. But again, that's just some basic terminology that we'll be using. And when we deal with sequences, we're going to need to deal with sums and products. And there, I've just shown you the basic sum and product rules. Okay. Now I want to talk a little bit about analog and digital signals. And what I start out by doing is I remind you of the definition of open and closed intervals, and introduce probably the idea of half closed intervals. And a lot of times in signal processing, we're going to be using closed intervals because we're interested in the endpoints. But I also warn you that a lot of people are sloppy, and sometimes it's going to matter as we'll see. But anyway, that's just the notation. So analog signals have a continuous set of possible values. Digital signals correspond to a discrete set. And a common example of digital signals are binary sequences where we only have zeros and ones. So we'll see that quite a lot. The basic thing is if we've got a continuous time signal and it can take any value on the closed interval, including the points at infinity, then the continuous signal is called an analog signal. If it can only take, if we've got a discrete time signal, that can only take on a finite number of values. And so that's what we'll call a digital signal. We're also going to be dealing with the real and complex signals. So a signal is a real signal if its value is a real number. It's a complex signal if its value is a complex number. And in general, in engineering, we denote the square root of -1 not as I, but as J. And even more complicated, in a lot of instances, I is equal to -J. So and we'll look at some ramifications of that later. But J is going to be our usual thing. We'll use I for summations and things like that. So signals can also be deterministic or random. Deterministic signals are those for which the values are completely specified for any given time, and they can be modeled by known functions of time. Random signals take on a random values at any given time, and if we characterize them, we have to do it statistically. We'll spend most of this semester on deterministic signals. We will, right at the end, probably look at a few random signals. Something else to be aware of is, I think you're aware of the idea of odd and even functions. And so the idea carries over into signals. And basically, I've just stated the conditions for odd and even signals. And you can read those. And I then go on and state the condition for a continuous time signal to be periodic with period t, and you can see the definition. We'll talk about the fundamental period, which is the smallest value for which the periodicity holds. And most of the time, we'll be working with fundamental periods. I point out that constant signals are not periodic, and most of the time when we're dealing with a constant signal, we'll call it a DC signal. Well, remember, DC is just direct current, and basically the definition fails because there is no smallest value of t for the constant signals. We can expand these ideas to discrete time signals, and we can have sequences representing discrete time signals which are periodic, and I state the condition there for you. And let me point out that if we've got a signal or a sequence that is not periodic, we'll call it aperiodic mostly. Sometimes we'll call it non-periodic. And something I will point out here, which we'll meet later, is that it's possible to do uniform sampling of a periodic signal and to find that the sequence isn't periodic. Well, the next thing that I go through is a sequence of examples on periodicity. And I'm not going to talk you through these. These are things that you should work through with a pen and pencil. So I guess the how-to for today is mostly going to be making sure that you understand the 5 examples, and I would go through and make sure you understand each of them. I think there are 5. I'll probably end up being wrong, but anyway. So there's a variety of examples, and they're all about really periodicity functions. Yes, when I was saying it, I thought I ended up doing more than 5 examples. There's an example 6, and probably well, that's it. So make sure that you read through each of those examples. They are important. We're going to be using the ideas from here on in, but a good use of the equivalent of your class time today will be to go through each of those examples with a pencil. And it's the sort of thing, I've written all of the steps in there, and the important thing is not that I go through them, but that you go through them. So make sure you do those examples. At the end of this section, I introduce the idea of energy and power signals, and I remind you how we define power, basically in terms of a current and a voltage. And I point out that in signal processing, it's better to use a slightly different definition for power. And what we do is we define the power, the instantaneous power per ohm, and it's also denoted by the power signal, but it is our usual power divided by R, and so we can then write the total energy, and we can write the power on a per ohm basis. Well, in fact, they're both on a per ohm basis. But anyway, we can then generalize those ideas to arbitrary signals, and we use that to define energy signals and power signals. Though this little piece is tacked on at the end because when you're reviewing, it's a good place to look at it. But we won't actually use the idea of energy and power signals for at least a couple of weeks. So while I suggest that you read the last couple of pages, really the things that I want you to do and the things that we'll keep using in the next few days are the things that end at the end of the examples. So make sure that you work your way through the middle of page 13, and that then concludes our basic introduction to the idea of the basic ideas of signals and systems. So I'll quit at this point. The notes will also be available to you, and you could actually just read through the notes if you wanted. But anyway, I'll stop screen sharing at this point. And what I'll point out to you is that I do want you to do one other thing before next Tuesday's class. So what I'm actually going to do is I'm going to do the actual how-to intro to Python live in class, just to make sure that we all get it. But what I want to do is I want to show you where to go. So I'm going to start my browser. And then what I'm going to do is I'm going to share my browser screen. So let's go back to screen sharing. I typically use this browser called Brave, which has some nice security features, which blocks most advertisements and has the great advantage of having Tor built in. But anyway, what I'm going to want to do now, though, is just show you the Google Colaboratory. So we're going to go to Google, and I'm just going to find it for us. So we'll go to Colab, and so this is the Google, or it shows us the Google Colab or the Colaboratory. We'll click on the link, and it takes us to a place that's welcome to Google Colab. I've used it before, so it shows the notebooks that I have available. But what I want to do first is I want to cancel out of this and just go to the welcome screen. So what I'd like you to do is go to the Colab and just read through these welcome pages and look at the getting started and see what it takes to do basic things in Python. And let me point out that if you click on a piece of code here, so if you notice, there's an empty box in the seconds in a day calculation here. If I go to the line, what happens is an arrow comes. If I click on that line, it tells me that the cell hasn't been executed in this session. It's just left over from a previous session. So I'm going to just run it by clicking on that arrow, and you can see it will run. It's in the process of running. And with a bit of luck, it won't take too long to run. It will give us the answer. Of course, it's still running, and there it ran. It usually doesn't take that long. So that ran that first piece of code. I can now go down to the next block, and I can do the same thing, and I can run that piece of code. And again, it's running. So if I wanted to, at this point, I could delete the cell. I'm not going to, but you can do all sorts of things, and you can introduce text boxes like this. But if you go through, it tells you you can write in LaTeX. It shows you some more examples, and what I'd like you to do is to try a few of your own things in this. And the reason that it says cannot save changes, by the way, is I'm running one of their programs rather than one of my own. So if I get out of this program, so I've left the site and gone back to Google, and I'm going to start it again. And if I start it again, it'll bring up the one of my own sets of notebooks. And so I'll just show you what it might look like. So this is one that I've done. I'll probably give you access to this one, but it just shows you in this case how to load information from from your Google Drive and so on. And if I run this one, it would basically link my Google Drive and allow me to read things from it. But those are the sorts of things that I'll do in class. And actually, what's shown in this one is how to get information out of a data frame. And it looks like the data frame that I was using, well, the data frame I was using was the passenger list for the Titanic, but anyway, we'll use a signal data set next week, but it just shows you some of the things you can do quickly, plotting information about the data set, and then doing more formats of that. But basically, I just want you to read through the introduction and to show you can really quickly get to doing some really advanced things. And in the second piece, I basically imported some sunspot number and showed how it changed over time. We'll learn how to do these things, but I just wanted to show you what Google Colab looked like, and to tell you that I'll be using it in class on Tuesday. So please familiarize yourself with it before next Tuesday. Actually, if you don't have a Google Mail account, well, actually, you've all got a Google Mail account. You've got a UCA email address. Recognize that gives you a Google Drive, and if you haven't found it, find it, because the easiest way to use Google Colab is to put any files that we develop on the Google Drive associated with the account that you're using. But again, we'll explore that on Tuesday. I'm going to stop the sharing. and I'll say goodbye. You've got enough work to cover Thursday. We'll pick up some of the ideas next week, but next week we'll get into the real practice, because mostly what I've talked about so far and the examples are about definitions. But anyway, I'm going to stop the recording at this point.